Hey guys! In this video, we're going to be continuing our conversation on exponentials, namely how to graph them. Namely how to graph them, as you could probably tell from the functions. Okay, remember, whenever you see the word functions, you're going to be graphing them. Okay, so in this PowerPoint, it's really important to remember all of our exponential rules because we're now going to be using them to actually graph the equations. All right, when we are graphing exponential functions, the thing to remember is this notation right here. I don't know if you can see that. No, you didn't. All right, this notation right here. So the equation is y is equal to ab to the x power. So a few things I want you to notice off the bat. Number one is that b is the base. Okay, b is our base. And that's going to tell us a lot, so make sure you pay attention to b. Number two, our exponent is the variable. Okay, it is x. So when we plug things in for x, we're actually plugging that into the variable. Okay, so it's very important that you remember your exponent rules coming up here. And then we have a. You may or may not remember a from earlier in the year when we had y is equal to a times x minus h plus k. Okay, this a is the same a that's down here. So we're going to bring back a, h, and k in this video as well. So don't forget about those. But let's move on. So first off, the base. Oh, come on. The base is the constant, and the exponent is the variable. You may have already filled this out, but I'm going to fill it out with you. Okay? Exponential functions are nonlinear. Okay, exponential functions increase and decrease at a very rapid rate, as you'll see in a moment. And so they are not linear, they are nonlinear. This is actually the first nonlinear graph we've gone over so far. Now, down here at the bottom, you see different examples of exponential equations. Now, notice how the base is always in parentheses. Okay, this is because, like I said earlier, the base tells you stuff, and so it's always a good idea to leave the base off by itself. That way you can see it and translate it easier going into the graph. All right, so here is an example of an exponential function. And this is actually, as you'll find out in a moment, an exponential growth graph. Why is it growth? Well, because it's going up. Ta-da! All right, but the way exponential graphs happen, like I said, is when you plug in for x, you're plugging into the exponent. And so that's going to change how the relationship works. So let's work out these first few. So our function is y is equal to 3 to the x power. Now you can already kind of see the table right here, but I'll do a little bit over in this blank space so that you can follow along as I'm doing it. Now, we pick these 5 points right here, -2 through +2, because it's a nice, good set, and it will give us, we know from experience, nice, neat numbers. The existence of the 6th 1/2 is to make a point that I will make in a moment, okay? But typically, -2 through 2 is a good set of numbers just to pick. It's a good default because that gives you typically a good spread of the graph. All right, let's get started. So when I take these numbers, take x, I'm going to plug it into my equation. So I have y is equal to 3 to the -2 power. Okay, well, remember our exponent rules. Negative exponents send the base to the bottom. So this is actually going to be 1/3 squared, which, as you can see over here, ends up being 1/9. Let's do another one. We've got y is equal to 3 to the -1, and that'll just be 1/3, as you can see. Okay, over here, when you put 0 in the exponents, remember anything raised to a 0 power is 1, and that's where 1 comes from. Now the 1/2, here it comes. Remember, whenever you have anything raised to a fraction, this is actually √3. Now, the table gives you the decimal approximation to make your graphing life easier. But just so that you're aware, whenever I ask you for a radical, I don't want the decimal approximation. I want you just to leave it as a radical. Okay? Keep life simple. All right, so then we keep moving on. We plug 1 into our exponent, 3 raised to the power of 1 is 3. And then when we square it, 3 squared ends up being 9. Okay? And so if you're looking over here at your y's, you can kind of see the pattern start to form. 1/9, 1/3, 1, 3, 9. You can start to see a pattern. And then when you plot it, you can see how the points start out nice and slow, nice and shallow slope, but then it gets really steep really quick over here in this general area. And that is the trademark exponential function. It goes from being a nice shallow slope to all of a sudden a really, really steep slope. Okay, now reading the question, let's talk about the vocab words. We have our y-intercept and our domain and our range. I'm going to erase some stuff. Now, the y-intercept should be an easy one to remember. The y-intercept is where the graph crosses the y-axis. Where does it cross the y-axis? Where x is 0. Which means that this is my y-intercept right here. Now, exponential functions won't always cross at y is equal to 1. Okay? Well, if the graph gets moved or transformed, that'll change where it crosses. But if you just have y is equal to the number to the power of x, so technically y is equal to b to the x, you don't have a or anything else happening, then you're going to have a y-intercept of 1. So y-intercept is 1. Okay, on to domain. Now the domain of this graph is actually really easy. Remember, domain is all possible values of x. And as I look at this graph, I have the arrow going this way to infinity, so x goes to negative infinity over here. And then it goes up going this way, which means positive infinity over here. So for exponential graphs, my domain will always be all real numbers. Or to express it in interval notation, negative infinity to positive infinity. Okay. The range is slightly different. The range, remember, is all possible values of y. Now, in this graph, my range is 0 to positive infinity. Okay? In this graph, it will never go towards negative infinity, and here's the reason why. Notice how right here, my graph gets really, really close to the x-axis, but it never really crosses over. Here, I'll erase so you can see it better. Okay? The graph gets really, really close to the x-axis, but it never actually crosses over. And if you doubt me, plug this equation into your calculator and play around with the x. Okay? Plug whatever number you want into it, positive or negative. The graph will never cross the x-axis. When you have this type of thing, okay, where you have a spot the graph will never touch, it'll get close to it, but it won't touch, it's called the asymptote. Asymptote. Now what the asymptote is a spot on the graph, or a spot on the graph where the function approaches but never actually crosses. Or touches. Okay, like I said, when you plug this in the calculator, you can plug in negative 1 million. It will never cross the x-axis and give you a negative y. The reason for this is because your negative is in the exponent. And remember, negative exponents end up creating fractions. They move the base to the other side of the fraction. And so what you'll end up getting if you plug in more and more numbers is progressively smaller and smaller fractions. But you won't get a negative answer. Y itself will never be negative. And that's a unique thing about exponential functions, and it's something you'll explore a little bit more as you go into higher math. Now, I mentioned it a little on the last slide, but there are two types of exponential functions. You have growth functions and you have decay functions. Now, the difference between growth and decay, aside from the obvious going up and going down, is b. Okay, remember I told you on the first slide, pay attention to b. Here's why. Now the general equation, as a reminder, is ab to the x power. B is my base. If b is greater than 1, then you're going to have a growth. Okay, notice how it won't ever be 1. But if b is greater than 1, then you're going to have a growth graph. If b is less than 1, but greater than 0, then you'll have a decay graph. Okay, so a good thing to look at when you're trying to decide is this growth or decay just off of the equation is first check b. If it's greater than 1, you have a growth. If it's less than 1, but greater than 0, then it's decay. All right, and you can kind of see a few things that we already talked about on here. The only thing that we haven't directly addressed yet is the end behavior, but I'll get to that in a second. What I first want you to do is just look at the pictures and notice what a growth graph looks like and what a decay graph looks like. Okay, now the reason why they call it growth and decay will be obvious. The growth one rapidly shoots up, whereas the decay one rapidly comes down. Okay, but remember, we read this, or we do math the same way. We read from left to right. So when you're trying to decide whether it's growth or decay, always read from left to right. Okay, do the vertical line test, do whatever. If going from left to right, it's rapidly going up, it's growth. If it's rapidly going down, it's decay. And that's the first test you can use. All right, end behavior. Remember, end behavior is how the graph is behaving, what it's doing as it goes off into infinity. So over here, for my positive, my growth functions, as x is getting smaller, so as x goes to negative infinity, because that's where it's going towards negative infinity, y is approaching 0. Okay, it never actually goes over 0 because of the asymptote, but it approaches 0. On the other side, when x is going towards positive infinity, well, y is also going towards positive infinity. Okay. With the decay functions, it's kind of a backwards flip. All right, as x approaches negative infinity, y is going up. It's actually approaching positive infinity. And then down here, as x approaches positive infinity, y approaches 0. Again, it doesn't go over or ever actually touch because of the asymptote. Okay? And the asymptote is actually, when we start graphing this, is a very good thing to keep an eye on because it helps just sketch out where the graph could be. Let's keep going. Now, this is an exponential growth function, and as you can see, the one we worked on a few slides ago is a growth. Okay? Now, in this one, a is positive. So if I were to rewrite this, remember my equation is y is equal to a, b to the x. B, obviously, is 3. Okay, but a is actually 1. I have a positive 1 right here. So, hypothetically speaking, what would happen if a is a negative 1? All right, let's look at that. So if I have a as a negative 1, what it's going to do, and I'm going to do it over here, so I have y is equal to negative 3 to the x power. Okay, you're still going to have your growth graph, but what happens is that the negative, a being negative, flips it over the x-axis. So it's going to look like, whoops, wrong thing. It's going to look like this, and it'll go down. All right. So it's still a growth graph because b is still greater than 1. But when a is negative, it flips it over the x-axis, and now it's going down. Okay. So this is what a growth graph looks like when a is equal to positive 1 and when a is equal to negative 1. Or just any negative number. This could be negative 2, negative 5, doesn't matter. A little bit on decays. Again, remember, keep an eye on b. It's not about whether it's positive or negative. It's about whether it's greater than 0 or greater than 1 or less than 1. Okay. So in this one, we have a is positive. And as you can see from right here, a is positive, y is equal to 1/3 to the x power. And you can see what happens when you plug in negative numbers for your exponents. This one only gives you 3 points just to give you the general sketch. Remember, negative exponents, flip the base to the other side of the fraction. So when I have y is equal to 1/3 to the negative, or negatively squared, it's going to be 1 to the negative 2 power, 3 to the negative 2, and that's going to cause it to flip. And so now I have 3 over 1, or 3 squared over 1 squared, which ends up just being 9. All right, and that's why it's flipped the way it is. A couple things to notice. Notice the y-intercept is still 1. Okay, it hasn't really moved, it hasn't transformed or changed. It's just b to the x. That's all it is. Whenever you have a b to the x graph, it's going to go through 1. Now, this is when a is positive. Let's briefly go over what happens when a is negative. Okay, so if I had y is equal to a negative 1/3 squared, or to the x power, okay, it would start out as you see over there, like this, and then the negative bit, the negative a, would again flip it over the x-axis, so it looks like this. My red graph is what happens when a is negative. And over here, a is a positive 1. And again, it doesn't have to be a negative 1. It can be whatever negative number. But when a is negative, it flips the graph over the x-axis. All right, let's keep going. And this time, we're going to do one ourselves. So first, we're going to draw our table. And we're going to use those same 5 points at the beginning. So we're going to use -2, -1, 0, 1, and 2. And again, the reason why we're using these 5 points is because they'll give us a good snapshot, you could say, of what the graph will look like. All right, what I want you to do now is pause the video and do the table. If you want to go ahead and start graphing, excellent, but the video is going to pause, and when it plays again, you'll see my filled out table. Here we go. Check with your table, see how you did. Now when you're filling out the table, don't forget your exponent rules. Negative exponents move the base to the other side of the fraction. Okay, that's why my 1/2 raised to the -2 and the -1 flip the fraction, and you end up getting regular numbers, 4 and 2. Okay, video's going to pause again. Go ahead and graph these points. Okay, here's my graph. Again, you want to make sure that this piece of the graph does not dip below the x-axis. Remember, the asymptote is there and nothing goes below it. Now, if you wanted to add a few more points to your chart, or if you already did that and see what happens over a bigger space, that's fine. But we're going to answer the next pieces of the question now. So I have the y-intercept, the domain, and the range. Video is going to pause. Please locate these 3 pieces. Okay, and you can see my answers down there in blue. The y-intercept is 1. The domain is all real numbers from positive infinity to negative infinity. And the range is from 0 to positive infinity. Now notice that on my domain and range, I used interval notation. Okay, bringing back interval notation. Remember, interval notation, when you have parentheses, it means that the graph never actually touches that point, which is why we use it on infinity. But notice the range. I used a parenthesis on the 0 because of the asymptote. The graph approaches 0, but it never actually touches 0. It never actually gets there. So that will always be a bracket. Okay, let's move on. All right, now that we've graphed an exponential function, let's talk a bit about the exponential behavior. In a sense, what exactly is happening. Okay? Last semester, when we talked about linear functions, we learned that they have a constant rate of change. This constant rate of change was called the slope, but the fact is that it either increased or decreased at a constant rate. No matter where it was the exact same rate. Exponential functions are not linear, okay, and therefore they do not have a constant rate of change, but they do have a consistent ratio. And what this constant ratio is referring to is, in fact, b from our equation of y is equal to a times b to the x power. Okay, the constant ratio is referring to b. All right, let's explore this. Now, on this picture, first off, we're going to examine the graph, or the table really. We want to determine whether the set of data shown displays the exponential behavior. Again, we're not looking for a constant rate of change, we're just looking for a pattern. Now, two things you have to first see. Number one is that the domain values have to increase or decrease at regular intervals. Okay, check and make sure the x values are increasing or decreasing at a constant rate. Because otherwise, if you go from an x value of -10 and then your next point is all the way in the positives, okay, yeah, that's going to throw off your ratio. So make sure your domain values are increasing or decreasing at a constant rate. Okay, now we're going to look for a common factor among the y's. So checking my x's, and yes, my x's do increase by 5. So we're good. We can go ahead and check the bottom. Now my y's, when I look for this, I notice that they all decrease. The whole thing is decreasing. Let's see, 4 to 2, this is divided by 2 or times 1/2. 8 to 4, also times 1/2. 16 to 8, also times 1/2. And you can begin to see the pattern. And here it is even down here, spelled out a little differently, that the y values are decreasing by a rate of 1/2, or you're multiplying it by a rate of 1/2. Now here's where it differs from slope. The domain values are at regular intervals. Okay, that's a +5. However, the range values differ by a positive common factor. So both the x and the y's are increasing at regular rates. However, the x's are being added, +5, +5, +5, whereas the ranges are being multiplied. Okay, and that change is what causes the exponential behavior and what makes this a ratio and not a constant rate. Okay, so my common factor is 1/2, and if you look down here, this is what is equal to y. If I were to graph this function, I would have y is equal to 1/2 to the x power. So my common factor ends up being my base. And that's one of the reasons why you got to watch B for whether or not it's a growth or decay graph, because the ratio will tell you whether you're growing or whether you're decaying. Now, that was the table. Let's look at the graph itself. Now, this is not the same graph as our function as the one from before. As you can see, the y-intercept is 64 and not 1, which y is equal to 1/2 to the x power would give you. So this is a different graph. However, it is still an exponential graph because of the curve. Okay, we go from really steep points to a really smooth curve. And pause on this one. The smooth curve bit is an important thing to know. Okay, remember when we went over absolute value? It was a V shape. Okay, this is not a V. There are no sharp turns. It is a curve. It has to be a nice, smooth curve. Back to the graph itself, we can see that as y decreases, x is increasing. Or you can flip it around and say as x increases, y is decreasing. This is an exponential behavior where the base is in between 0 and 1, which means it is a decay graph. This is exponential decay. Now that might have been obvious just by how it looks, but it's always good to remember that the base is in between 0 and 1. Before we move on from the slide, I want to review end behavior. What I want you to do is figure out the end behavior as x approaches negative infinity. What is y doing? And then as x approaches infinity, what is y doing again? Okay, video's going to pause. See if you can figure out what y is doing. How'd you do? So remember, end behavior focuses on what the graph is doing as the function continues off into infinity. What are our points doing? In this particular graph, as x approaches negative infinity, so if I were to take my calculator and I were to keep plugging in negative values for x, what's happening to my y values? And what's happening is that they're getting bigger. So as x approaches negative infinity, y approaches positive infinity. Okay, because the numbers keep getting bigger. On the flip side, if I start plugging in positive x values, okay, as x approaches positive infinity, what happens to y? Well, as you can see, the function approaches the asymptote down here. Okay, the asymptote is again the x-axis, and y approaches it but never goes across. Now, the asymptote will not always be the x-axis. Okay, we'll talk about this next time, but when we have the equation y is equal to a times b x minus h plus k, okay, this is the transformation notation or transformation equation for exponential behavior. You may remember A, H, and K, and I assure you they have the exact same jobs they did last time. But for right now, I just want to talk about K. K is the asymptote, all right? I'm going to abbreviate it like that. Whatever K is, that's where your asymptote is. So that makes it easy to spot, because when you look at the equation, you can just see right off the bat whether or not y is going to approach 0 or y is going to approach 5 or whatever other number. So just to give you an example equation up here at the top, if I have y is equal to 1/2 to the power of x, that's the equation from the last slide, there is no k. Technically, this is plus 0. Therefore, my asymptote is 0. Whereas if I were to have y is equal to 1/2 to the power of x minus 5, okay, well now k is a negative 5, and so my asymptote is going to be at negative 5. And we'll get more into that next time, but I wanted just to bring that up because what we're going to do now is identify graphs based on the equations. Okay? Now, as you can see, all of these graphs have an asymptote of 0. Okay, all of the graphs approach the x-axis and do not go over. And as you can see over here on the equations, there is no k. So all of these have like a plus 0 at the end. Okay, so right now we're not moving the asymptote around, but we still need to be able to identify what graph goes with which one. Now, the two big tricks when you're doing this is to look for your base and to look at A. Remember, the base tells you whether it's a growth or decay graph. A flips it over the x-axis, okay? Or it just flips it. It's a vertical flip. Sometimes it's not the x-axis. So what we're going to do is, fact number 1, this graph is above the x-axis, so A needs to be positive. And it's going positive. Okay, this is a growth graph. So I'm looking for an equation where A is positive and I have a base that is greater than 1. So as I check my options, it has to be this first one. This is number 1. Because my base is greater than 1 and A is positive. Okay, what I want you to do, the video is going to pause. You guys do the next 3. When it plays again, check your answers. And here are my answers. So on numbers 3 and 4, where the graph, where A is negative, sometimes figuring out whether it's growth or decay could just mean mentally flipping the graph back up. Okay, it's easier to see it when when A is positive, whether it's growth or decay. And so whenever you do have A is negative, just kind of mentally flip the graph back up and see whether it's growth or decay from that picture. All right, guys, this is all I have for you. I shall see you next time. Bye.